Um, Thank you very much, Archak and Professor Patwardhan, for giving me a podium to speak in this very nice event. Um, and sorry for the confusion. You will definitely get to interact with Leena as well in the afternoon when she shows around some of the cool labs that we have in systems and control. So I'm a professor in the Center for Systems and Control. I'm also the head, so I wanted to probably talk a little bit about the department as well, just a couple of slides. Um, so that's the building, right? Not far from here. So we have a fairly large set of diverse set of faculty who focus on many different areas connected to control, robotics, autonomous systems. This is, you can see many in this word art like space GNC, reinforcement learning, aerial space robotics, underwater robotics, learning, adaptive systems, optimization, and so on and so forth. So a lot of these are obviously fairly well connected to the notion of connected autonomous vehicles as well. A lot of the research that in fact goes in is also applied to mobile robotics platforms, which are again very close to what you have in modern day vehicles. Yeah. So this is anyway, I wanted to also show you a glimpse of the faculty that we have. As I said, we have a very diverse set of faculty with fairly funny profile pictures, I must say. But anyway, fairly diverse. Everybody is somehow connected to either control, learning, optimization, uncertain systems, robotics, ground and aerial vehicles, cooperative and distributed systems as well. So a lot of going from a lot of classical control to modern distributed parameter systems, cooperative systems as well, including quantum systems and optimization. We have a fairly good experimental and hardware facilities. You will see some of them in the afternoon. And we have a fair amount of industry interaction and commercialization pathways as well. Some of the sponsored projects and industry projects, I'm not going to focus too much on it. The basic point being that I think there was a lot of discussion on the involvement of ministries and private entities as well. So we have had a fair amount of interaction with entities from different ministries as well as private companies on the consultancy side. I also wanted to sort of bring, I think I saw Sandeep present EPGD, so I wanted to put in this as well. We are also planning to propose, we are already in the proposal stage for a EPGD program in controls and autonomous systems. This may be fairly well aligned with the kind of algorithmic ideas, at least, that will go into cooperating systems that are talking to each other. And if you want to achieve maybe different tasks using these systems. Now, in a typical road scenario, it would not be achieving tasks, but everybody wants to do their own thing. But still, there is a certain concept of competition and collaboration. So all of these ideas we would like to put together in a sort of 6-course structure, 6 to 8 course structure. I mean, we've not completely finalized the whole program yet, but yeah. So it basically looks at different ideas such as the vehicle model itself, then the idea of how to control it, how they talk to each other, what are the sensors, what is the hardware that's involved. So we want to introduce a little bit of all of this in this EPGD program, and that's the idea. And we would definitely like inputs from this forum because we do feel that this is fairly well connected. I think some of the interactions we had with the group from Germany also, it looked like they were coming from a controls and to an extent a background which was partially cooperative systems and game theoretic ideas and things like that, also going into some of the algorithms that were getting used. So that's where probably we see ourselves fitting much better in this entire space, where we look at competing and collaborating algorithms of vehicles that are talking to each other. And that's so in my lab, so which we call Laboratory of Aeromechanical Autonomy, a lot of focus on aerospace and mechanical systems. So I'm sort of providing you some of the work that we do in cooperating systems, which is again something to do with connected autonomous systems as well. Some of the work that we've done in the past is on platooning. You can see on the right, where you essentially want these logistical highway delivery vehicles to. This is very common in Europe and US, where you are doing a lot of platooning for high throughput logistical delivery systems. So we work on a lot of this platooning ideas. On the left, you have this basically more of a robotics sort of a. We also try to understand if you have cooperative systems and you want them to do something together, what happens if there are errors in this network? Yeah. So one of the things that we want to also understand is, can I figure out, can I do some, some good task? For example, this is a task where you can think of, you have an asset, more like a defense-related task, where you have an asset that you want to sort of monitor and you want to make sure you are circulating around it. And you start with some errors in the network, right? And so the idea is, in spite of the fact that I started with some errors in the network, I'm still able to, get to a formation, what we call a formation in our community. The idea is basically that I can do, I can execute certain tasks without being concerned so much about what are the errors in the network, because I can actually identify those networks given some good algorithms that are running on them. So most of the algorithms that you're seeing here are also distributed, so they're all running individually on each machine. One of the other problems that we are working on with, again, some industry partners as well here is on automated intersections. This is one of the problems that fascinated us a lot. The idea was that a lot of the research, so of course coming from the application perspective, we know the signal in front of IIT Bombay is like an inspiration for all of us. Anyway, because everybody who comes to us says, oh, that's one of the toughest intersections to cross, right? But research-wise, we know that, we saw a lot of background research from Europe and US, where everybody's talking about very laned traffic. Everybody's following in a lane, and then they come to an intersection, and then the only decision they have to make is when to stop and when to leave. So it's really, very, I would say, very, very sanitized problem that they're working with. But then, we are working with unregulated laneless traffic, right? So, yeah, so obviously, so then we started looking at some algorithms. We, again, because we are algorithmic people, so we really started to work on algorithms which said that we are not following any lanes. Yeah, we are simply going to do whatever we want, start wherever we want. Just the only thing I know when I get out of the IIT gate is I know which point I want to reach. And I somehow have to get to that side, right? So now the question is, can I automate it to an extent? Yeah, and so we actually showed with some, some algorithms which are based on some Lyapunov ideas, you would know, yeah, some fun Lyapunov ideas, some barrier ideas. And actually we presented this at a learning conference, optimization learning conference, and they were fairly happy that it scales quite well to see that, you can see that you can get from some start point to some end point, and this is based on some optimization problem that's running, again, on board. So you're of course assuming that your vehicle has fairly decent onboard processing, but then with all the, again, the Waymos and all the, automated vehicles, that's not such a big deal, yeah, having a good processing.
You are developing algorithm for this, or are you using some other?
This is our algorithm, yes. Yeah, we've developed this algorithm. We've developed the algorithm, we've presented the algorithm. We've not put it on a vehicle and tested it yet, but yeah, that's that part we've not done yet. So we are mostly very algorithmic guys, but we test them to an extent as well. So then one of the issues, again, we continued to work on this. One of the issues with the previous algorithm was it was still solving an optimization problem at every instant. And so some people tend to say that, okay, in real time, can I actually keep solving these optimization problems? It's fairly hard. So we wanted to focus on a different set of algorithms which doesn't solve any optimization problems, right? So here, it's also very similar simulation actually, it's not very different. You actually, I'm not sure if you see, but you start from some crisscross things, but you end up in the same color, right? That's the idea, yeah. And you can see that they sort of make a circle around each other. It feels very much like, what you would be doing in a very real traffic situation, yeah. You're sort of, and the cases that we are showing you here are fairly the tougher cases where you're literally like trying to cross each other. You start here, you go here, this guy wants to start here and go here, and so we are sort of showing you some of the tougher cases, so you see that they circle around each other. And these ones are now not based on optimization, they're based on some prefixed laws or ideas where you are basically have some sensors like lidars and so on to figure out where your neighbor is or where the other vehicle is, and then you are basically acting based on that. Yeah. So again, this one also seems to scale fairly well. We also do a bunch of other things, because obviously a lot of things that we do with vehicles and with mobile robots and aerial robots requires us to use vision, and so we are also working on a fair bit of vision-based navigation. Yeah, so one of the interesting problems that we are working on is in this lunar lander-based navigation, which is based on some crater maps on the moon. So this is something that, again, inspired by the ISRO's mission. We wanted to use some crater maps to actually localize your lander, because when the lander is actually around the moon, it no longer has GPS and so on. It's a GPS denied area, so how do you localize yourself? And so we actually created this simulation on a gaming engine, and you can actually, so these simulations that you see on the top are basically on a gaming engine where a moon map is sort of superposed, and you are using a real camera that's in the gaming engine. Like, gaming engines are actually very good. I'm not sure if any of us are playing games, but neither am I. Okay, excellent. So, but gaming engines have really good real world view. This is on the Unreal Engine. Yeah, so this is on the Unreal Engine. Yeah, so these are very good because they use actual cameras and actual, when you play some of these games, you will see that they're very realistic. So we use that to do this navigation experiments. We also developed some hardware in our lab, again, because we want to test some of these ideas, not particularly related to connected autonomous vehicles, but we are fairly capable of, we have things like these flapping wing aerobot. Somehow the labels got flipped. Yeah, so that's the one on the bottom right is like a flapping wing drone that we are sort of building. The top left is a fairly simple 2DOF system that we are writing codes for from ground up for control. And the one on the top right is what you're seeing in actual testing of a manipulator on a drone. It's basically picking up some juice box and then sort of going back down and sort of a delivery sort of system, if you may. We have enough a decent bit of exposure. I've not put any of the government grants, but we have industry partnership with TCS Research, Tata Advanced Systems, John Deere Tech, Inspacity, and so on, and several international universities. So a fair bit of exposure in that sense to the kind of problems that are probably of interest to other academics in the world and as well as industry. So we hope to contribute in a very positive way here as well. All right, I think that's it. Thank you.